All right, welcome to Lab 3. May the Lord be with you. This lab we're going to be studying capacitance. And capacitance is how much charge you can put on a conductor for a given amount of voltage. And if you recall, voltage is related to work. So whenever you have a power supply and it's turned up to a certain voltage, that means it can perform so much work per unit charge. So if you want to put some charge on a surface and you want a certain value for the charge, then you could figure out, okay, what is the capacity of that surface? And then you could figure out, oh, then I need to apply this voltage, and then I'll get that kind of charge on there. All right, we're going to look at two capacitors. One is a spherical capacitor, and this is this device right here. We're actually going to collect all the data for the experiment this week in the lab here. There isn't a simulation online that allows us to get really good data and also give you the experience like you're really doing an experiment. So you're going to be watching these videos, hopefully over and over again, until you fully understand them, you can analyze the data, and then write up the lab report. The first experiment's very straightforward. It's kind of weird when you see just one little ball here that this is a capacitor. But it turns out that this is just one plate of the spherical capacitor, and then the other plate is the entire room. And the room is so big that it doesn't matter if it's off-centered. It's still enormously far away, the other plate. And basically how we do that is we just plug the other end of our experiment into ground. So surrounding this inner plate is this ground, which would be 0. So it's going to be positively charged. So surrounding this whole thing is our power supply ground, which is acting as the second surface. For the second experiment, we're going to use this. This is a standard capacitor. This is they call it the basic capacitor. And this allows you to change the distance between the plates. You can't change the plate size, but you can change the distance between the plates. All right? And to give you something to think about as we go through all the information, what we're going to do is we're going to put 30 volts on here, which will put so much charge on the plates when they're about 1 millimeter separated. Now, it's really nice. On the inside here, you can see those little white spots. Those are insulators, so the two plates won't touch each other and short out. So when you close that thing all the way up, it has a separation of about 1 millimeter. And we're going to put 30 volts across there, and that will put so much charge on the plates for this particular capacitor. Then we're going to disconnect the power supply, and we're going to move the plate out like this, and we're going to measure the voltage between the plates. Now remember, it was 30 volts when it was right here. Put the charge on there, and then we remove the power supply. So the charge is still on there, no more power supply. And I'm going to take my hand here with these guns right here, and I'm going to pull that apart like this. And so the question is, what's going to happen to the voltage across the plates? And you can see I've got one lead that's going to go to my voltmeter, positive, and the other lead over here, negative. Okay, so those are the two capacitors we're going to study. But before we do that, we need to talk about conductors in general. So I have a spherical type capacitor here, but it has a hole in the top. Okay, so we can go inside there and investigate what the charge is inside that hole, and we can also investigate what the charge is on the outside. Then we have the experimental version, and I'm just going to put that over here because we'll save that for the experiment. And then the other one is this metal surface right here that's shaped like Snoopy, and we're going to inspect what the charge distribution is on this surface when we put 2,000 volts on it. So for 2,000 volts, this has this, and so much charge is going to come onto this surface. And then it'll just stop. It'll be at 2,000 volts, and it'll have that much charge for this capacitance. But the question I ask you is, this is a conductor. And in your preview PowerPoint, you have a whole like 4 or 5 slides where you have to understand the properties of a conductor. Conductors are a lot different than insulators because every atom of metal allows one of its valence electrons to move around. And remember, we're talking about electrostatics here, so when I hook this thing up to the power supply and the charge races out to the surface, it'll do it in about 10 to the minus 16 seconds. It's crazy how fast it creates a charge distribution. Then I'm going to sample the charge on the nose of Snoopy here, on the back of his head over here, and then on his snout, on the side of his snout. So what you should be hypothesizing right now is if this is a conductor and there's charge on here that's not moving, what will the charge density be? Now charge density, so I can move to my next slide here. Let me flip to the next slide. I have my pointer here somewhere. Where is that pointer? Huh. Must be up here. Here it is. All right. So charge density is how much charge there is per unit area. Now, if you have a nice spherical surface like this, then the charge will uniformly distribute itself all around. So if we measure how much charge is on a little area over here, or over here, or over here, we would suspect that we would get the same value. All right? Now, when we measure this thing, we use what's called a proof plane. And this is the object right here. This has a handle that has super high insulation. So if we put some charge on the end of this thing where the metal surface is, it will not conduct through the handle. It'll just stay put on that little metal plate. Also, the back end looks black, like an insulator, but it's not. It's actually a metal that happens to be black. So maybe it has a lot of carbon in it, because carbon's a really good conductor. So there's a carbon surface here, and again, with the insulating handle. So we can actually go inside this ball and analyze what kind of surface charge there is inside this metal surface. Okay, now remember, when you let charge go on a metal surface, the charge will almost instantly distribute itself and stop. Well, that means when it stops, there's no forces acting on those charges. So the net force between all these like charges that hate each other is zero. Another thing with conductors, if you go inside the conductor, the electric field is zero. Because if the electric field wasn't zero, it would make the charge on the surface move around again. But it's static. Static electricity on conductors, totally different from insulators, arranges itself until there's no net field inside the conductor, and that results in no net forces on the charges on the surface. So we're going to go ahead and we're going to test the charge distributions on these surfaces right here. Now we have the Faraday cage from experiment number 1, and recall we measured the charge on that little sphere. So we put charge on the sphere, and then we dipped it in the Faraday cage, and we measured the voltage, and then multiplied by the capacitance. If you recall, we used the LCR meter to measure the capacitance of the Faraday cage and the electrometer. That was approximately 0.150 nanofarads. Okay, so by the way, farad is the unit of capacitance. It's a coulomb per volt. All right, so we're just going to look at the voltage for the various situations here. This electrometer is so sensitive that it just picks up. There's the littlest amount of charge in the room right now because we've been messing around with the equipment before we did this video. So it actually makes it record some voltage even when we don't have anything turned on. Now I'm going to take the power of 2,000 volts right there, and then the other end of the capacitor is the room again, and you can see I got that hooked up to ground right there. So this is the ground port, and it's hooked up right here, and then this is positive. So this would be positively charged in relation to ground. And it's shaped like Snoopy, not like a sphere. So the questions you want to ask yourself, where do you think the charge density is going to be the biggest, and where do you think it's going to be the smallest? Now the biggest will produce the biggest voltage, and the smallest will produce, the smallest charge distribution will produce the smallest voltage. All right, so we're going to turn this thing on and let it go up to 2,000 volts. Okay, we're just about there, and I need my little ground wire. I don't see what did I do with that? Okay. All right, where is it? All right, we're just going to go ahead. I'll just use my body. Remember, my body's see, it's already at 24, and we haven't done anything. All right. So I am going to just touch this thing. You can see it's at 0. And I'm going to touch the side of Snoopy's face right here, right along his snout. And when I do that, I want to make sure that this surface is tangent to the surface of the conductor, and we'll get a pretty good sample of the charge density right there on the side of Snoopy's face. We plug it in there, and you can see I got 4 volts. Okay. All right, so now I'm going to discharge it, and also I want to get rid of the charge that's on the proof plane. And I'm going to go to the back of Snoopy's head right here, touch that, and make sure everything's nicely zeroed. And I plug that in, you can see I'm getting like 5, 6, okay, it went up to 7. All right, so here, I'll do it one more time. Yeah, 5 or so. So the side of Snoopy's face was 4. We'll do that one more time. Yep, 4, right on the money. And then we're going to do his nose, his wet nose right there. And stick that in there. And you can see it went up to 9, pushing 10. Okay, so you can see the charge density on the front of his nose is bigger than the back of his head, and then the least over here. And it's related to surface area. So you can see this side over here has the smallest surface area, so the charge needs to bunch up to create a counter field for the charge that's going to be on this side. So if there's plus charge over here, their field lines are generally going this way, and if there's plus charge here, they're going that way. Well, there's a much larger surface area, so the charge density be less, so it's equal. So when you add up all those field lines, they cancel out with a lot more charge here that's pointing that way. And then this has the greatest radius of curvature, since it's nice and straight, so it's going to have the least charge distribution. And it's basically canceling the electric field in this direction right there. Okay? So now let's go to the next metal surface, which is the ball with the hole in the top. So we're going to sample the charge inside, and you could be asking yourself while I fix this this alligator clip, what is going to be the electric field inside the conductor, the conducting surface. All right, so we'll sample the outside, and then we'll sample the inside. Is that up to 2,000 there?
Oh, yeah.
Okay. Hey, I just got a shock off that thing. It's crazy. Okay, 30 volt shock. All right, so let's go ahead and sample the outside. And that's up around 8. We'll do it one more time. Here, I'll do it over here. And that says 5, 6. All right, let's do it one more time. Let's do it in the front. And it says 5 right there. Okay, so that's a charge density there. I'm going to go inside now and sample. So I turn it over. I'm going to use a little black ball and touch the inside. And I'm going to come out. Oh, hold on one second. It's going crazy. I'm getting a lot of charge on my body, so I'm really messing the thing up. All right, but you can see nothing. No voltage at all. And we can do it one more time if you'd like. Zero. Pretty nice, huh? That's why you're protected inside your car. So if a thunderstorm comes up, you do not have to worry about being electrocuted, which means you're going to die. in your car. Because the electric field, due to the electrical storm out there, is 0 inside your car, because your car is completely surrounded by a metallic surface, and the electrons always rearrange themselves until they stop moving. But that means that inside that metal body of your car, the electric field is 0. All right, so that's to get us started, and this is also to get you give you a background in how to deal with surface charge density. Because when we do the experiment on capacitance, we can't measure all the charge on this sphere right here. What we do is we just sample this guy right here, get this charge, put it in here, and then we set up a ratio. We say, okay, the surface charge density, now the symbol for surface charge density is lowercase sigma, and that's equal to Q over the area. So this will be the area of the proof plane, and then this is the charge on the proof plane. But since I took it off of the sphere, it's going to be in the same ratio as Q on the sphere divided by the area of a sphere. Now the area of a sphere is 4 pi r squared. And the area of a proof plane is pi r squared. So you got to keep into account that this is just a disk, and then the other thing is the spherical surface. So that's how we determine how much charge is going to be on our capacitor when we do the experiment. All right. So I got a couple more slides to go over as far as capacitance goes. And this is a spherical capacitor. So when you hook up a battery to 2 spherical surfaces, the inner one's positive. That's what ours is going to be. Ours is going to be positive. And then the outer one is negative, and for us, that's ground. Now capacitance, this is the definition of capacitance. It's how much charge you can put on 2 surfaces per unit volt. Now when I mean 2 surfaces, I mean one is positively charged, and then the other one has an equal but opposite negative charge. Okay, so a capacitor always has the same charge Q, but one surface is positive and the other one is negative. So then whenever they say, hey, what's the charge on that capacitor, they're just talking about the absolute value. It'll be the charge on one plate. Now, if you use Gauss's law, and again, that's not our lab topic, so we're not doing that here. But if you use Gauss's law, then you could determine the electric field between these 2 surfaces here, and then figure out what the voltage is, and then plug that in the formula, and it'll give you this formula right here. So it's the radius of the inner sphere times the radius of the outer sphere divided by Coulomb constant, and then the difference of the 2 radii. Okay? Now, RB right here, this is going to be infinity. So if you take B out of this equation, you end up with A over 1 minus A over B, and when B goes to infinity, A over B goes to 0. And so this thing just disappears, and you have a really simple value for the capacitance, and it's equal to A over K. But K is also equal to 1 over 4 pi epsilon naught. So you can flip that upstairs, and it turns out to be 4 pi epsilon naught times the radius of the sphere. So it's a really simple formula, and you're going to be testing that in the experiment. So that's the spherical capacitor. All right. Now, let's go to the, by the way, I will, each week when we do these experiments, I'll be including these little PowerPoints so you can go review back and see what I did in the video to go along with the video, so you can review it a lot better. All right, now this is a parallel plate capacitor. So the 2 plates are parallel to each other. They have an area A, plate area A. So again, when they say the area of the plates, it's not twice the area of one plate, it's just the area of one plate. Because this plate's going to have a positive charge, and this plate's going to have a negative charge. And then it's separated by a distance d. This is a square plate. In our experiment, we're going to have a circular plate. All right? Now, when you actually buy a capacitor, They don't look like this. What they do is they make it like using foil for the conductors, a foil material, and then they put a insulator between the two conductors, and that's called a dielectric. In our experiment, air is our dielectric. So you see all around here, surrounding my sphere is air, and between those plates over there, the air only have air in there. But we could like stick we could put notebook paper between the plates and then measure what that effect has on the capacitance as well. But we're not going to be doing that in this experiment. All right? But anyway, that's what a real capacitor looks like. And it's basically this thing rolled up into a cylinder. All right, that is it. So the next video, we're going to do both experiments for you, and we're going to do each experiment individually, because we need to get the equipment out of here and then bring the other set of equipment in. You've probably noticed in these 3 experiments there's a lot of equipment involved, and so when you have your materials list, you're going to have a long list of materials. Okay, so that's it, and we'll see you in 1 second with the spherical capacitor lab. Thank you.